In this part, we will establish our first bounds on the crossing number. First, we want to look at complete graphs. We won't prove anything here, but I want to show you some very interesting results and conjectures. The first one is by Guy from 1960. He showed that the crossing number of the complete graph Kn is at most 1 over 4 times n over 2, n minus 1 over 2, n minus 2 over 2, n minus 3 over 2. Now how can we interpret this number? If we pick any 4 points in the drawing of Kn, there are 3 pairs of edges here that could cross. The green ones, the red ones, or the blue ones. But this is only if they are in convex position. If they are not, then none of these pairs cross. So the question basically boils down to Sylvester's 4-point problem that asks, if we have a point set, then how many subsets of 4 points are in convex position? And here the interpretation is that at most 1 of 8 of those is in convex position. So for only 1 of 8 of those subsets of 4 points, we will get a crossing. And a very big conjecture is that this bound is actually sharp. This has been proven for up to 12, and no counterexample is known yet. For 12, this is 150. For complete bipartite graphs, a similar bound is known due to Zarankiewicz and Urbanik. And here we have for one partition n over 2, n minus 1 over 2, and for the other one the same. This is basically where the whole problem where we want to minimize the number of crossings comes from. This question, what is the crossing number of complete bipartite graphs? And this study began during the Second World War with Paul Terran. He was working in a brickyard and he was wondering how to design an efficient rail system from the kilns to the storage yards. For every kiln and every storage yard, there was some track that connected them. The problem was that whenever 2 tracks crossed each other, then the bricks might fall off the cars. So he was considering how to lay the rails to reduce the number of crossings, so that they reduce the number of bricks that fall off the cars. And this is what motivated the study of the crossing number of graphs. For the rectilinear crossing number, there are lower and upper bounds that also don't match yet. For the lower bound, we have almost the same, but there is a plus epsilon here. That means that the lower bound for the rectilinear crossing number is already bigger than the upper bound for the crossing number. And the upper bound is slightly larger. While this is 0.375, Eichholz et al. Could improve it to 0.3807. Here we know the exact numbers for n at most 27. You can check out the webpage of Osman Eichholzer. There he shows for, I think, up to 120 points what is the current known lower bound and what is the current known upper bound and what is the point set that realizes this current known upper bound. Now let's move away from complete graphs and try to find some lower bounds depending on the graph. And the first lower bound we will establish is if we have a graph with n vertices and m edges, then the crossing number is at least number of edges minus 3 times number of vertices plus 6. This should ring a bell for you. Whenever you see 3n and a 6, this is what comes from the planar graphs. Planar graphs can have at most 3n minus 6 edges. And it's not a coincidence that this shows up here, because we will use that in the proof. So assume we have some drawing of G with a minimum number of crossings. We will obtain a graph by planarization, so we will turn the crossings into dummy vertices. So for every crossing, we add a new vertex, and 2 edges get split into 2. So if we do this for every crossing, then the number of vertices we have in the graph H is n plus number of crossings in G, and the number of edges is m plus 2 times number of crossings in G. And now what we have here is a planar graph, so we can apply Euler's Polyhedra formula. And that says the number of edges, which is m plus 2 number of crossings in G, is at most 3 times number of vertices minus 6. And now if we look at this formula, we have an m here, that's that. We have a 3n on the right side. If we pull it over, we have minus 3n here. We have minus 6 on the right side. Pulling it over gives us plus 6. And here on the right we have 3 CR of G, and on the left we have 2. So pulling this over, we get crossing number of G on this side. And that's already the proof. We can get an even better bound. Namely, we can show that it is an omega of m squared divided by n. More precisely, if we take the largest planar subgraph of G, and we say the number of edges in this planar subgraph is r, then the crossing number is at least r times m over r choose 2. How do we do this? So we want to partition the graph into m over 2 edge-disjoint subgraphs that have at least r edges each. Now we want to get lower bound, so let's just assume that all those subgraphs are drawn planar. Now I want to look at 2 of these subgraphs. Each of them had at least r edges. We know that if we pick any r plus 1 edges, then the graph is not planar anymore, so we require a crossing. Now pick any edge of a subgraph Gj and add it to another subgraph Gi. Then this is more than r vertices, so there's more than 0 crossings. Now we do this for every edge of Gj. There are at least r of those. So every edge, each of those r edges of Gj introduces at least one crossing with at least one edge of Gi. So for any 2 subgraphs, we have at least r crossings. And how many pairs of subgraphs are there? Well, there are m over 3 subgraphs, so there are m over 3, choose 2 of those. And how do we get to this part? Well, r is an order of n, so we have an n here, and this whole thing is an order of m squared divided by n squared, so we get this bound.